Assalamu alaikum. The maze search algorithms are naturally very exciting AI algorithms to study. However, a real challenge is creating large and good looking mazes rather than the mazes like these. The mazes like these can be good to study one algorithm, but what if you want to test the algorithm on a bigger maze like of size 100 by 100? Of course, you cannot create bigger mazes like these. This requires to use some GUI framework and usually the object-oriented programming approach. But not everyone, especially the beginners, are comfortable especially with the GUI programming and maybe also with the object-oriented programming. So this series is aimed to overcome this issue in a way that anyone with the basic level of programming experience in Python will be able to develop any maze search algorithm without the need to have the experience of GUI development or the object-oriented programming, and still getting the good looking and scalable to any size mazes as you are watching on the screen. How's that going to happen? Basically, I will introduce a module I have written for this purpose, and that module will provide you with all necessary, very simple to use functions to create and customize the mazes. And then you can implement any search algorithm like depth first search, breadth first search, A star, some reinforcement learning, some genetic algorithm, or any other you could think of without worrying about the GUI part and the maze generation, and focusing just on the AI algorithm. The simulation you just saw was just these few lines of codes, which are basically using the functions of the module I mentioned. I'm Mohammed Hassan Naeem, your instructor for this series where we will study amazing algorithms. In this first lesson, I will introduce how to use the module so that you can create and customize the mazes. And then from the next lesson, we will start implementing different algorithms. So let's get started. The first thing you need to do is go to the GitHub repository that I have provided in the description and copy this code, which is about 900 lines at the moment and may get updated by the time for more features. Create a new file in your working folder. I'm naming it as pyamaze.py and I will copy that code here. You don't need to know what's happening inside this code. You just need to follow the next step about the use of this module. I have created 4 classes in this module that we will be using. So create any new Python file and let's import the first important class, which is named as maze. I'll pause the video for a moment for one clarification. After the video had been recorded, I decided to upload the module as a Python package, so you could install that and don't need to copy paste the module code every time. I tried to upload the package with name pyamaze, but this name was not available, so I uploaded the package as pyamaze. You can download the package as pip install pyamaze, and then you can import that easily as from pyamaze import maze, and there are a few other classes in the module we will see in a while. So if you are copying the code from the GitHub repository, you can name the file anything you want, but you can also download the package as pyamaze and then use that name. Thanks, and let's continue the video. Now let's create a maze object by simply using the maze class. This will create a maze object and the default size is 10 by 10. Then on the maze object, I will apply the method createMaze to generate a maze. This could be done while creating the maze object, but there are many customizable parameters that we will explore in a while, so I decided to have a separate function for this. In the module pyamaze, the GUI framework being used is Dijkstra, which is built in Python and you don't need to install that. Also, just for the information, inside the maze class I have implemented the maze generation algorithm, which is known as recursive backtracker, to generate the maze. The last statement of our program will be applying the function run on the maze object m. Let's run the code. And you can see this 10 by 10 randomly generated maze. Every time you will run the code, you will see a new random generated 10 by 10 maze. Let's see how different parameters of this maze we can access in our program. A maze is composed of cells and those are indexed as row number and column number. This indexing is very similar to matrix indexing, with top left cell as the first row and the first column and bottom right as the last row and the last column. Then this highlighted cell, which is 1 1, is actually the goal of the maze. This generated maze is a perfect maze, which means that there is only one path from this goal to any of the cell inside the maze. Therefore, I have not highlighted the start cell of the maze because any cell can be treated as the start cell. However, internally the bottom right cell, which is the last row and the last column, is the start cell of the maze. So by default, the target is to search a path from this cell to this cell, but we will see shortly that if we want to change the goal or the start cell of the maze, we will be able to do that very easily. Moreover, instead of the perfect maze, which is having only one path from the start to goal, we can generate a maze having the multiple paths or the loops within the path. So let's see different options we can use while generating the maze. Firstly, instead of 10 by 10, we can generate maze of any size by specifying the size as row number and column number while creating the maze object. For example, 15 by 20. This is a 15 rows and 20 columns maze generated. After the size, we can specify different maze properties inside the create maze function. The first two of these are x and y. These specify the cell xy be treated as goal and default value is 1 1. Let's set the goal as cell 4 4. And see that now the goal is the cell 4 4. Now I will use the default goal and the next optional argument is pattern with the default value as none. Let's set its value to h in lowercase or uppercase where h stands for horizontal. I hope you can see the effect that the generated maze has longer horizontal lines. So that is what is meant by the pattern being horizontal. Instead of h we can have v for the vertical and this time the generated maze has longer vertical lines. I will set the pattern back to the default value none and the next optional parameter is loop%. This parameter specifies the percentage of loops, meaning the multiple paths inside the maze. If you are solving a maze on a paper, it's easy if there are many multiple paths, but with the computer algorithm, the loops can be tricky as the logic can get stuck into never-ending sequence. So we can create the maze with multiple paths by setting the value of loop% parameter, which is having the default value as 0, meaning 0% loops in the path, meaning the perfect maze, and we can set it to some greater value, and 100% means the maze generation algorithm will try to introduce maximum loops in the maze path. Let's try the loop% 50. And you can easily see there are many loops in the maze path. Loop% 10 means there will be lesser loops. 100 means there will be maximum loops and you can see those. Then the next option is save maze with the default value as false. And you can make it true and it will save the maze for future use. Why we need this option? Many times it happens that while testing the search algorithms on different mazes, it works perfectly, but suddenly it fails on a specific maze because each time a new random maze is generated. Now you have to investigate that particular maze again and have to retest your algorithm on that. This option will help you on this. If this option save maze is true, the generated maze will be saved as a CSV file and you can use that file to regenerate that very maze. Let me show you that. The maze has been generated. Try to memorize the maze a little bit. Let's just keep in mind this reverse L shape here. I have closed the maze, but see that inside the working folder we get a CSV file named as maze followed by the timestamp the maze was generated. If you see this CSV file, the first column header is cell and the value is cell numbers like 1121 etc. And then are the columns EWNS, which is for east, west, north and south. These refer to the 4 directions and the values are 0 or 1. The 1 means the maze wall in that direction is open and 0 means that wall is closed. You don't need to change anything, and if you want to regenerate the same maze, you need to use the option load maze and provide the CSV file of that maze. This is the same previous maze being generated every time. See this reverse L shape here again. Another good thing about this feature is that you can customize the maze manually. For example, if I just want to remove this wall from the maze, then I can do it by changing the CSV file. See that one wall is actually a wall between two cells. For example, this wall is blocking the south of the cell 12.1 and the north of the cell 13.1. So I'll have to change 2 entries of the CSV file. These are the values of EWNS for the cell 12.1. The last 0 is for the south showing that it is blocked. I will change that to 1. Then the north of 13.1 should also be opened. This second last 0 is the north of the cell 13.1. I will change that to 1 as well. Now I will run the code again and see that the wall has been removed. So you can customize the maze as per your needs. Just keep in mind that for each wall to add or remove, you have to change 2 cell directions. Also note that when the maze is loaded from the CSV file, the size of the maze here does not matter because the information along with the size is loaded from the CSV file. One last optional argument in create maze function is theme. The default value is dark and you can change that to light. In the pyamaze module, the first class is named as color. Here I have defined a few color objects we can use for our maze. The first is dark and the value is a tuple with the 2 names of the colors. Gray 11 is the color of the background and white is the color of the maze lines. You can search for the Dijkstra color chart and will easily get some chart like this with the names of the different colors you can use in Dijkstra. The second color object is light with two values, white for the background and black for the maze lines. Then are few other colors that we will be using for some other purpose, and you can very easily add more colors here if you want to follow some other color scheme. So here in the theme option with the default value as dark, you can change that to light. For that I will import the color class from the pyamaze, and then here I will specify the theme as color class object as color dot, and you will get the IntelliSense help for different colors inside the color class. Let's choose light. And now the maze theme is light theme. Instead of specifying the value as color class object, you can specify that as string as well. So that's all different options for the maze style and color etc. I will get back the default values, and now it is a 10 by 10 perfect maze in dark theme. Now the next class we will use is named as agent. The agent can be thought of as a physical agent like a robot placed inside a cell or just to highlight some cell. This will be used to simulate the path planning like the path being traversed in this simulation. Let's see how we will use this. We will create an agent, and the first required argument is parent maze, which is the maze inside which we want to place the agent. I will specify the maze M we created on line number 2. The other parameters are optional. If I run this, see that an agent is placed at the last cell of the maze. So the agent by default will be placed on the last cell. If we want to place that at some other cell, we can specify the cell as input argument x and y, for example 5, 5. And the agent is placed on cell 5, 5. For the agent object, it has attribute x and y that we specified as 5 and 5 while creating the agent, and we can later access that using the .x and .y. Let me just change the y to some other value. Then there is another parameter named as position, and this is one two-value tuple as the value of x and y. See x and y and the position value. Actually, we can change these parameters after creating the object. For example, let's change the position to 510 after it was created at 5, 5. And see that agent is placed at 510 and not at 5, 5. So we can change the position of agent after it has been created. The next optional argument is shape. We will see that a bit later. The next option is goal. The default value is none, which means the goal of the agent is same as the goal of the maze. But if we want to change the goal for the agent, we can provide that as a tuple here. We will use this in next lesson. The next argument is named as field. Its default value is false and I can make it true. See that the size of this agent is large and it fills the whole cell. Now let's see the argument shape. Its default value is square and we can assign another value as arrow. You will see an arrow shaped agent now. This feature is added for the cases when the agent will be a physical agent like a robot. In that case it has front side and other three sides, and to distinguish clearly this shape is introduced. If the shape of the agent is arrow, the argument field is meaningless. Whether it is true or false, the size of the arrow will be same. The next argument is footprints with the default value as false. Let's understand its use. When footprints is false and we change the position of the agent, like instead of 5, 4 it is changed to 5, 5. Let's see what happens. We see the agent at 5, 5 instead of 5, 4 because the updated value is 5, 5. But it's very likely that we want to see the track of the path of the agent. For that we will make the footprints true. And see that here, this is the current location of the agent and this is the impression of the footprint. There is slight difference in color shade of the actual agent and the footprint. Let's update the position of the agent a few more times. See the three footprints and then the present position of the agent. The same is true for the arrow shape. The two colors you see as agent color and the footprint colors are coming from the color class. The default color of the agent is blue and its value is the tuple with two Dijkstra colors. The first one is the color of the agent and the second is the color of the footprint. These colors are defined and you can create more colors if you want. The last option for the agent is color, having the default value as blue, and we can set that to some other color defined in the color class. Now the agent color is green. Again, instead of color class object, we can set this as a string. So we have seen both maze and the agent class. We can create a maze and place the agents on it. The next important thing will be making the agent move on a specific path. If you see different methods and attributes of the agent class, many are starting with underscores. That means those are used internally and you should not use those. If you see the maze object, it has many attributes other than underscore attributes. Let's see those. Rows attribute is the number of rows of the maze, which for 10 by 10 maze is 10. Similarly, columns is the number of columns of that maze. Then is the attribute grid. If you print that, it is just a list of all cells of the maze. Then a very important parameter to implement any search algorithm is maze_map. This specifies the detail of open and close walls of the maze. See that it is a dictionary with keys as the cell of the maze and the value is another dictionary. For cell 11 value is this dictionary where the keys are east, west, north or south. The value of east is 1 and 0 for the remaining 3 directions. See in this maze for cell 11 only the east direction is open and the other 3 are closed. And if you see this last cell 1010, only north is open. See here only north is open for the last cell. Then is an attribute path. This maze generation algorithm not just generates a random maze, but will also provide the path detail from any cell to the goal cell of the maze. In later videos, this is something we will be generating by the respective maze search algorithm, but the maze class also has the path information. The path attribute is a dictionary with keys as one cell of the maze and the value as another cell of the maze. For example, if key is this cell, the value will be this cell, meaning that if the agent is on this cell, it should move to this cell in order to approach towards the goal. For example, this is first entry, key is 12 and the value is 11. It means that if agent is at 12, it should move to 11 to reach to the goal. Then the key is 13 and value is 12. So if the agent is at 13, it should move to 12 and so on all other key value pairs. Now how to make the agent move on this path? Let me first remove all optional arguments of the agent. Now in the maze class there is a method tracePath. As input argument we need to pass one dictionary, the key will be the agent and the value will be the path, which for this case will be the path attribute of the maze. The agent by default is placed on the last cell, which is 1010 in this case, and the path attribute has the information to move to the next cell from the last cell, and then the next cell from that cell, and then the next cell and so on until the goal is reached. The function tracePath will implement that. See that agent is moving towards the goal. It will be good if I make the footprints equal to true. Let's also see field equal to true. Now the interesting thing will be the arrow shape. See that it also simulates the turning of the agent as well. Let's see if we have multiple paths in the maze. Let's check with the square shape. This path is the shortest path of the maze. So the solution of the maze is the shortest path from the start to goal. In this tracePath method, there is optional argument delay with the default value as 300 millisecond, which is the delay between moving from one cell to another. Let's make it 100. See that the speed is high now. Then another argument is kill with the default value as false. If we make it true, the agent will disappear after 300 milliseconds after reaching the goal. Then one last argument is show marked with the value false. So let's make it true. The use of this parameter is to indicate some specific cells. For that we have to set some cells as marked cells parameter of the maze. and if the agent will reach to any of these cells, that will be marked. These are 4 cells. Let's run this. Two cells have been marked which were inside the list and the agent reached to those. These options have been added for some better explanation of different algorithms that we will study from the next lesson. We have seen an agent can trace a path provided as dictionary. We can also specify the path as list of cells and also as a string of direction steps. And also there is a possibility to have more than one agents on the maze and also to move those on their own different paths. Let me create one more agent. Now I will copy just a sample path as a list of the cells. It means that agent will follow these cells from first to the last in the list. Inside this dictionary of agent and path, we can provide more agents and paths as other key value pairs. It means now two agents will follow their respective paths. Let me change the starting location of the agent B to 55 and then it will follow this path. Maybe you noticed that this agent crossed this wall. It is because we provided a sample path without considering the walls. But in search algorithm development, we will consider that algorithm should consider the wall. There is also a possibility that I use the trace path method 2 times and provide one agent path pair in both. In this way, the first agent will complete its path and then the second will start. And we can also use different values of the optional input arguments. Now the third option for the path is a string with the movement steps provided as east, west, north or south. Let's create a third agent. And here provide another agent path pair. See that 3 agents followed their own paths. And now they will move after one completes his path. Let's apply kill equal to true just for the first agent. There is one last class I have added in the pyamaze module. It will not take much time. It is the text label and will be used to display some text results on the output window. The first input argument is the parent maze, which is M, and then we need to provide the title and the value to be displayed. For example, title is total cells and the value is product of rows and columns. See that total cells 100 displayed here. You can provide more than one text labels and all will be displayed. However, there is one limitation of these text labels. You cannot display the changing data on these text labels, like the timer or counter or the current cell of the sum agent. The reason is the way Dijkstra works is that it will execute everything and in the last statement all results will be simulated. And the text label will display the final value of that variable. So that's all we will be using for the next lessons for the different search algorithms. The general approach will be developing a function for a particular search algorithm and that would be returning the final path. Then we will create the maze as described in this lesson and then we'll use the trace path method to trace the agent on that path generated by the search algorithm. I know there are many functions in this pyamaze module, but you will see these will make the codes of the future lesson very simple and easy, allowing us to focus just on the search algorithm. You can get these codes provided in the description and also see the detail of the module provided on GitHub. At the end, I will show you 2 more very simple functions which are in the maze class and we might not be using those in the search algorithms, but they can be interesting. and that is to control the agent through the keyboard keys. For that, there is a function named as enable arrow key. As input argument, we will pass one agent. Now this agent can be moved using the arrow keys. I am using the arrow keys here. Now I'm pressing the up arrow key, but you can see agent is not moving up because there is a wall in upward direction. So there are checks applied to move the agent only when the path is open. You can also control the agent using the keys WASD using the function enable WASD. This agent is moving with the arrow keys, and now I'm pressing WASD keys to move the red color agent. For these two functions, I'm using the 4 functions to move the agent, and I have applied the checks to first verify if the path is open. So that's all from this lesson, and if you find this useful, please support me by hitting the like button and don't forget to subscribe to the channel. Also check other content on my channel related to Python programming, machine vision, PLC programming, instrumentation and sensors, etc. Thank you very much.